Now we are going to get into section 1.6 in your book. This is the section on closed and open sets, so I suppose I had better tell you what a closed set is. So let's let F be a set of real numbers. Then we say F is closed if whenever you've got a sequence of numbers that are all in F, so a sequence of points in F, and that sequence of numbers converges to some is a convergent sequence, that is, it has a limit, it has some point, some real number it converges to, and it's the set F is closed if whenever this happens, your limit point X is also in F. And we say that G, a subset of the real numbers, is open. And I want to emphasize this. It's open if the complement of G is closed. It's a little bit confusing in notation. It's not that G is not closed. Not open doesn't mean not closed. Open means your complement is closed. So let us have a couple of examples. So if you take all of the real numbers, that is closed. If you take any convergent sequence of real numbers, if it converges to a real number, it converges to a real number, it converges to a point in that set. And similarly, the empty set is closed. If you take a sequence of points in the empty set, well, there aren't any points in the empty set. There aren't any sequences of points in the empty set, so none of them, if there's none of them, that counts as all of them. None of them converge. And notice that the complement of the empty set is all the real numbers. So the real numbers are both closed and open because the real numbers are the complement of the empty set. The real numbers minus the empty set is the empty set, and similarly the empty set is open because the complement of the real numbers is the empty set. The real numbers minus the real numbers is the empty set. So I want to emphasize we've come up with two sets that are both closed and open. You're allowed to have sets that are both closed and open. It's a strange situation. These are, in fact, the only sets of real numbers that are both closed and open, but they exist. So I'm going to mark someone down on the homework because they say that something is not closed, therefore it's open, and that's wrong. So make sure you don't make that mistake. So if F is finite, so something like F is, let's say, 0, pi, 3, and the square root of 2. Any convergent sequence, at some point if you take any convergent sequence in F, that means it's bouncing around among these four numbers, and eventually if it's a convergent sequence, eventually it's got to settle down. It's got to pick one of those numbers. So, of course, it eventually constant. It's got converged to a constant sequence. So, that is closed. And finally, the rational numbers, that is neither open nor closed. So we've got this sequence 3.1, 3.14, 3.141, 3.1415, 3.14159. That is a sequence of rational numbers that converges to I suppose we have not yet proven that pi is not rational, but you'll take my word for that, I hope. So we see we've got a sequence of rational numbers that converges to something, but the something it converges to is not rational. So rational numbers are not closed. And on the other hand, square root of 2 is irrational. And if you divide it in half or thirds or quarters, it's still irrational, is a sequence in the complement of Q, and this converges to 0, which is a rational number. That is, 0 is not in the complement of the rationals. And that means the complement of the rational is not closed, so the rationals are neither open nor closed. So those are a couple of examples of both closed and open, closed but not open, neither closed nor open. So the interval from 5 to 7, including the endpoints, is closed. If it converges to something, it's got to converge to something that's at least 5 or at most 7. And this interval is not closed. You've got the sequence let's say 6, and then 5.5, and then 5 1/3, and then 5 1/4. That sequence is obviously points in this interval, and it converges to 5. This interval, as it happens, is open. And I'll mention that proving that these closed and open intervals are in fact closed and open, that's going to be a homework or exam study problem, which is why I'm not going into more detail right now. we'd like another characterization of open sets besides the complement of a closed set. So here is a proposition that tells us a little bit about open sets. So let's let G be a set of real numbers. G is open if for every point X in G, there is a positive number epsilon. Epsilon is allowed to depend on both X and G, such that this interval from X minus epsilon up to X plus epsilon, that's the set of all real numbers where the distance from X to Y is less than epsilon, that thing is required to be a subset of G. And we're going to prove this using the contrapositive. That is, we're going to suppose that G is not open, and then we'll show that this thing that I've just labeled if a star with stars is false, and then we'll assume that the thing with the stars in it is false and show that G is not open. So let's suppose G is not open. That means that the complement is not closed. So there is a sequence of xn's that's contained in R minus G with xn is converging to x, x is not in R minus G, so x is indeed in G. Then what does convergence mean? So for all epsilon, any positive number epsilon, there is a natural number n such that the distance from xn to x is less than epsilon. That convergence means there's some capital N such that the thing I just wrote down is true for all little n bigger than capital N, but as it happens, we only need one n, so that's going what I'm going to write down. So xn is not in G, so that means that x minus epsilon, x plus epsilon, that is not allowed to be a subset of G because this xn is in that set. And remember, xn is a point in the complement. xn is not in G. So if G is not closed, not open, the condition star is false, And then by contrapositive, if the condition star is true, then G is open. All right, now we suppose that star is indeed false. So let's let X be a point in G, and let's write out carefully what that means. Let's be very methodical about it. So here's star. This says for every X in G, so this is a statement that's true for all X, and then we say there exists a positive epsilon such that and let's write this as for all Y in X minus epsilon, X plus epsilon, we have Y is in G. And so here's the negation. What does it mean for star to be false? That means that there is at least one an X in G such that, and then it is false, the whole rest of the thing has to be false. And then we have to negate the rest of this piece by piece again. So I'm going to be getting terser and terser. So there exists X and G such that. Now we're negating there exists an epsilon, so the opposite of it's true for at least one epsilon is it's false for all epsilon. So our there exists turns into a for all epsilon greater than 0, and then it is false that for all Y in our interval, we have Y is in G. So write this again. There exists X and G such that for all epsilon greater than 0, and then negating something that's true for all Y, we write this as there exists a Y in x minus epsilon, x plus epsilon, such that then the thing that's in green has to be false, and that's such that y is not in G. All right, so we're going to let x be the x that exists such that, and so on and so forth, because star is false. So we pick such an x. We know there's at least one such x. And then there might be more, so we just pick one. If n is in N, let Yn be, we take the interval x minus 1 over n, x plus 1 over n. That's an interval. We're basically taking epsilon equals 1 over n because we've got something that's true for all epsilon. Then there's necessarily a y in that interval that is not in G. So we're just assuming that this y, there's always a y in an interval like this. We're going to just let yn be the name of one of the ones in the interval from minus 1 to 1. Then x minus yn is always less than 1 over n, so pretty straightforward argument. Yn converges to x. Yn is not in G. So our sequence of yns that's contained in the complement of G, and x is in G, x is not in the complement of G. So the complement of G is not closed. So if star is false, G is not open. And by contrapositive, if G is open, then our condition star is true. And that completes the proof. Now we are going to prove something about what happens to closed and open sets if you take unions and intersections of them. So here's part A. So let's say I've got sets F1, F2 up through Fn. If those guys are closed, so is the union so is their union. F1 union F2 union F3. And then part B, on the other hand, if I've got a sequence of closed sets, so is the intersection, you can take either infinitely many of them, or you can take infinitely many of them. The intersection of infinitely many closed sets is closed. Part A is you need finitely many of them. You need a union of finitely many closed sets to stay closed. And it's going to be an exercise is to come up with an example of infinitely many closed sets that you union them up and you get something that is not closed. And then this situation with open sets is just the reverse. If you start with finitely many open sets, then their intersection is open, and if you take infinitely many of them, so is any finite union. You can stop after n of them, or you can go, or you can take infinitely many of them. So let's go ahead and prove this. I'm going to prove it a little out of order, I guess. So let's start with part C. Let's let X be in this union. So for each K, there is a positive number epsilon K such that this interval X minus epsilon, X plus epsilon is contained in GK, and that is by the previous proposition. I suppose your book does these propositions in the other order, but proposition 1.6.4 is just really useful, so I wanted to do it first. Now epsilon is allowed to depend on X and on the open set, so that's why I have to call it epsilon K, not just epsilon. So then we let epsilon be whichever of them is smallest. And since n is finite, if you take finitely many positive numbers, there's a smallest one of them and it's positive. This is why we can't do this with infinitely many of them. If there were infinitely many epsilon Ks, we would have to take an infimum, and you might have this situation where epsilon K is like 1 over K. So your infimum is 0. And then X minus epsilon, X plus epsilon. Let's go ahead and draw this thing on the number line. There's your X. There's X minus epsilon and X plus epsilon. And then epsilon K is bigger than epsilon. So we've got X plus epsilon K, X minus epsilon K. So that means that the interval from X minus epsilon to K to X plus epsilon K, it has inside of it the interval from X minus epsilon to X plus epsilon. So let's write that out. Which of course is contained in GK. For all K, so X minus epsilon, X plus epsilon is contained in the intersection of the GKs. And then to prove part A, you just use De Morgan's laws. So we've got, if you take the real numbers and you subtract off your union from your union of the f sub k's, by De Morgan, that's the intersection of R minus the f sub k's, and then each R minus fk is open. So by the thing we just proved by part C, that intersection of R minus fk is open. So complement of an open of a closed set is open, complement of an open set is closed. The thing I just wrote is the real numbers, the minus an open set. So that is closed. We're going to prove part B directly from the definition of closed sets. So let's give this thing a name. This intersection of closed sets that I am trying to prove is also closed, and let's let x, I can't call it k, let's let xn be a sequence in F. And then we suppose that our xn's are converging to some point x. So because this is an intersection, how about we stop at m if it's finite? So for each k, F, our intersection is contained in fk, so our sequence of xn's is contained in fk as well. And then fk is closed. So x is in fk for each k. So that means that x is in our intersection, which we named F. And so that means that if you've got a sequence in F that converges, its limit is in F, so F is closed. And finally, we're going to do part D. We're going to let G be our union. Either finite or infinite. And we let X be in G. And then because this is a union, we don't have that X is in all of the GKs, but we do have it's in one of the GKs. So there is a K with X being in GK. And then let's let epsilon be positive, be such that x minus epsilon, x plus epsilon is contained in GK. And now epsilon, this is just the epsilon associated with this GK, so you can call it an epsilon sub k. The point is GK, there is one GK that's open that has x in it, and therefore x minus epsilon, x plus epsilon has to be in it. So x minus epsilon, x plus epsilon, that's contained in GK, which is a subset of G because G is a union of all of these GKs. And this is true for all x in G, so G is open. And that proves all four of the things we wanted to prove, so we're done. And so, question I would like you to think about moving forward is, are our results B and D still true? The way they're written, they're these countable sequences of open sets. If we take, so what if we had uncountably many open or closed sets? So if we had intersection over F in some index set F, or a union of, if we had an intersection of open or closed sets, and here F, G are uncountable. So does it still work for uncountably infinite intersections of closed sets or unions of open sets?